Okay, now we'll talk about something that should be a little bit familiar. Maybe you saw it in middle school. It's exactly this here. Finding solutions to systems of linear equations. Okay. Keep in mind what we want to do here. We want to find an x value and a y value so that when I plug it into either of these, the equality is satisfied. Okay, so the left-hand side would equal the right-hand side. Now, there's many ways you could do this. For example, we might write one of these in terms of the other, one of these variables in terms of the other. So I could write my system like this. I'll leave that first equation like that. But maybe I want to subtract the y from both sides. And then I could sub this in there. So that would give me 3 times 8 minus y minus 2y gives me 4. And then distribute. I get 24 minus 3y minus 2y equals 4. Okay. I could rearrange this. I could subtract the 4 from both sides, combine these two terms, and add 5y to both sides. And then I would get 20 equals 5y. So then y is equal to 4. Okay, that's one way to do it. Another way is to just treat the entire equations as things we can operate on. So for example, I might want to add twice this row, so I can multiply this entire row by 2, and then add it to the first one. So I'm going to multiply this whole thing by 2, and then I'm going to add it to this one. Okay? You see what I get? I'll have 3x plus 2x minus 2y plus 2y and 4 plus 16. Okay. I could gather like terms. Those will cancel. I'll have 5x equals 20. Okay. And in both these cases, I can, of course, solve for the other variable. Here, if I sub this back into either one of the equations, I'd find the other variable. And the same here. If I subbed it into either of these, I'd find the other variable like that. Yeah, unsurprisingly, I get the same values for x and y. Doesn't matter which method I chose. Okay, what we're going to do is focus on this stuff on the right-hand side. This stuff here. Okay, and we're going to abstract it a little bit. Look at it in a slightly different context. Okay, like this. You notice what we did last time. Okay, I, for example, didn't touch this equation, but did multiply the second one by 2. Okay, so I should write the whole thing down like this. You notice that multiplication only affects the coefficients. So what I could do, rather than deal with the entire equations, I could just pick off the coefficients. So I have 3x, so I'll take that 3 here, minus 2y, so I'll put that minus 2 here, and 4 over here. Okay. Here the coefficient is 1. Same with right here, this is coefficient 1. And I can write those right here. So what I've done is taken this system of equations and then just turned it into this, what's called a coefficient matrix. Now, rather than deal with the equations on the left-hand side, all I need to do is deal with the coefficients. So, for example, I could multiply the second row by 2 and not touch the first row. multiply everything by 2 in that row, like this. Now, there's, of course, a reason why I'm putting these side by side. You'll notice that what I have on the left-hand side, the coefficients I have there, are exactly those numbers that are found in the matrix on the right-hand side. Okay. So rather than have to write out, the minus sign, the plus sign, the equal signs, and all that every time, I can just work at this level of the coefficients. Okay. Now, if you think back, you remember I added this second row to the first row, or I should say the second equation to the first equation. I can do that with these rows here. I can add the second row, which I'll denote by a 2 circled. I'll add that to the first row. If I do that, I have 3 plus 2, which gives me 5. Minus 2 plus 2 gives me 0. And 4 plus 16 gives me 20. Okay. And I didn't touch the second row. Okay. You can already see here on the first row, if I were to translate it back into an equation, I'd have that 5x equals 20. So x equals 4. That's what we saw on the last slide. But now I'm going to just take it a little bit further here. I'm going to divide the second row by 2, or multiply it by 1/2. Okay. I won't touch, actually no, and I'll also divide the first row by 1, or multiply it by 1/5, divided by 5. Then I have 1, 0, 4. The second one I've got 1, 1, 8. Now I'm going to subtract the first row from the second. Okay. What do I get here? Now I have 1, 0, 4. The second one, well, I've got 1 minus 1, so that gives me 0. Then I have 1 minus 0, leaves me with 1. And 8 minus 4, 4. Okay. I'm going to stop there with those row operations and reinterpret this in terms of a system of linear equations. The first one would read 1 times x plus 0 times y equals 4. And the second row reads as 0 times x plus 1 times y equals 4. Okay, so what you should notice here, on the right-hand side, I just deal with the coefficients. And once I get them down to this kind of form here, I can just reinterpret it in terms of the linear equations, and I've got my solutions. So this is another way to solve systems of linear equations. Okay, I left some practice for you here. I encourage you to do it. I'll just show you briefly how we might work on an even larger system. Okay, so this is a system of 3 linear equations in 3 variables. But just like in the 2 system with 2 variables situation, I can just pick off those coefficients and again, only deal with the coefficients. So I'm just picking them off like this. And now I can start working with it. Okay. The key thing here is you more or less can do whatever you want in whatever order. You just have to follow 3 rules. We can add one row to another. We can switch rows, or we can multiply a row by a non-zero constant. So, for example, I've got a 1 up here. Maybe if I subtract 2 times this first row from the second row, I'd get a 0 here. And then similarly subtract 4 times the first row from the third row, I would get a 0 here. Okay, just something I notice. So I could subtract 2 times row 1 minus 4 times row 1. Okay, and we'll talk more about what kind of choices you'd like to make when you're doing this kind of thing. But for now, you just get used to writing these coefficient matrices and just kind of playing with the row operations, just getting used to how it works. So here I subtracted 2 times row 1 from row 2, so I had 2 minus 2. Now I have 6 minus 2 times minus 1, that's going to give me 8. Then minus 1 minus 2 times 1, so that's minus 3. Then minus 4 minus 2 times 1, minus 6. Third row, I subtract 4 times the first row, so I've got 4 minus 4, minus 5, minus 4 times minus 1, so minus 1. Then 2 minus 4 times 1, so minus 2. And then 0 minus 4 times 1, minus 4. Okay. And you can keep on doing this. But this just gives you an idea of how we could write these systems, just in terms of coefficient matrices, and how we can operate on the rows and combine them and rearrange things that way. Okay, so as I said, there's really 3 rules to this. We can add one row to the other, so I can take this entire equation and I can add it to the first one. Okay, so if I just outright add it like this, then I would have 4x minus y equals 12. And I didn't do anything to the second equation, so I would just have this. But now if I did that in the coefficient matrix, you see what I'd get. I'd just have 3 plus 1, which is 4, minus 2 plus 1, minus 1, 4 plus 8, 12. Then down here I have 1, 1, and 8. Again, both sides, they're giving you equivalent results. And as we saw before, I can multiply an entire row by 2, which I can do here. I didn't do anything to the first row, but I did multiply everything in the second row by 2. Okay. And not surprisingly, if you work this out on the left, it would give you the same result. Another thing you can do is recognize that those equations are just written arbitrarily in that order. So I could switch them around if I really wanted to. Maybe seems like a silly thing to do, but it's going to turn out to be useful later. Oops, it should be minus 2y equals 4. It'll turn out to be useful later in working with these coefficient matrices. So I've got 1, 1, 8, and then 3, minus 2, 4. Okay? Fantastic. Those are the only 3 rules to this rearranging coefficient matrices game. As long as you do them, when you're working with a coefficient matrix, you can do them in any order that you choose, as long as you just stick to those 3. Okay? When do we stop row reducing? Well, as you saw last time, or a couple slides ago I should say, I kept on row reducing this until I got something that looked like this. Then I stopped. This form here, when I have that 1, 0, 0, 1, that's a special form called the reduced row echelon form. We want to stop there because we're thinking about translating this back to systems of equations. And if we were to translate it back, when we have this form, you can see that we only have x and y. So as soon as we have that reduced row echelon form, if we stop there, then we know what x and y are. It's just simply these entries here. Okay? So we're going to stop this process whenever we have that reduced row echelon form. Now, another question you might have is, can we always get reduced row echelon form? The answer is no. And we'll pick that up in the next video.